Hello, welcome to the last session on the topic of epidemiological approaches to causal inference. In this session, we'll talk about the more sort of quantitative approach and the quantitative underpinnings of how we make causal inferences. And these underpinnings are provided to us through the potential outcomes or the counterfactual model, the structural equations model, and methodological modeling. The potential outcomes framework provides us a way to quantify the causal effects. So up till now, the previous models that we have been seeing, the sufficient component cause model or the graphical models, they provided us a more qualitative perspective of the relationships between cause and effect. But then we have this framework of potential outcomes that can help us to actually provide us a set of conditions to conceptualize quantitatively what a causal effect could be. And so that estimate of the true causal effect for an individual and eventually at a population level is what is called as a causal estimate. And that is nothing but the change in outcome that we would expect to see or potentially see if there is a change in the exposure or the intervention, or in the presence of the exposure intervention, what is the outcome that you would expect to observe, versus in the absence of that intervention or exposure, what is the outcome that you observe. And if there is a difference in the outcome, help us to actually quantitatively estimate the causal effect. So this linkage, the conceptual linkage that the directed acyclic graphs bring us to understand how the relationships are between various variables, and the design factor of our studies, which we can understand through the counterfactual approach, provides that link between the conceptual framework and the mathematical link between the data and the estimation of the true causal effect. What is a counterfactual? So the key problem for causal inference is that when we do any studies or as such in nature, we observe the outcome for only one exposure status. So, for example, you could, again, just going back to the example of smoking and lung cancer. So, if you observe somebody or a population that smokes a certain number of cigarettes for a certain period of time, etc., you can see and then in whether what is the level of the outcome in terms of lung cancer in that population. But at that same time, we cannot see people who were on the population that if the same population was not smoking at that same level that we were seeing in the earlier, what would be the outcome, whether those people would get the similar levels of lung cancer or not in that population, right? Which is sort of, to be able to see this together is counter to fact. And why we need to see this together is going back to our definition of a cause, where we say that cause is defined as an antecedent event that is necessary for the occurrence of the disease or at the moment it occurred, with other conditions being fixed. And the only way we could fix these other conditions, which means nothing else changes except for the exposure, is through the understanding of what is known as the counterfactual. This is contrary or counter to fact that we cannot see both states of exposed and unexposed and then the difference in the outcomes at the same time. So it's counter to fact. However, this approach is very useful to actually help us to estimate causal effect, right? And how we design our epidemiological studies is the ultimate goal of the epidemiological studies, whether they are experimental in nature or observational in nature, is to quantify and get an unbiased estimate of the causal estimate, right? The causal estimate is a hypothetical or a figure where we could have calculated if we could have seen the potential outcome of being exposed and unexposed at the same time, right? However, since we cannot do that, we need to have comparison groups, right? And the way we have comparison groups depends on how we design our studies. So in experimental studies, the treatment assignment, right, we assign randomly assign treatment to our study participants. There will be a group of participants who will be assigned treatment or intervention, and there will be another group of participants who will be randomized to not receiving that particular intervention or treatment. And when we do randomization, what we expect is that this treatment assignment that we did is unaffected by any other variables that may be influencing the treatment per se and the outcome as well, right? So the difference in outcomes that we see in these two groups would be expected to be an unbiased estimate of the average causal effect in the population, assuming that your randomization is done appropriately, the sample size is appropriate, and so forth. However, we have a bigger problem in case of observational studies where the assignment of the exposure is not done randomly. We see what is already there, right? But we have what are called as comparison groups. So the design of observational studies, whether in cohort studies, we have two groups. We have the exposed group and the unexposed group. And then we try to see what is the outcome that is happening in the exposed group and what is the outcome that is happening in the unexposed group. So from the counterfactual approach, which is hypothetical, we're trying to create that counterfactual in real life. Similarly, in case control studies, we have two groups, but now the groups are on the basis of the outcome. See, are the outcome present and the outcome absent. And then we try to see what was whether exposure was present or absent in those who had the outcome compared to those who didn't have it. And then we try to make a causal inference, basically to see whether whatever difference that we are seeing in the outcomes when the exposure is present or absent, or in the exposure when the outcome is present or absent, is really a true causal effect or not. And the assignment mechanism, here we are saying the assignment mechanism for the exposure in observational studies can be considered to be unconfounded only after first identifying the confounders and then conditioning or adjusting on the observed confounders for which we have data on, right? And so valid causal inferences can be obtained in observational studies by adjusting the estimated treatment effects for the covariates through various mechanisms. We have the regression models, we have propensity score, and so linear regression, logistic regression, and various Poisson regression. So various statistical models that are at hand to adjust these known confounders and to get a valid causal inference. This brings us to the related approach to looking at causal inference, again from a quantitative aspect, which are the structural equation models. Right? So the structural equations can be viewed as formulas for computing the potential outcomes under various actions. So whether the exposure is present or absent, what would be the potential outcome, and to get a quantitative value of that causal effect is where structural equations help us to do that. Now here you see the directed acyclic graph that we talked about in the previous session, and then we can actually which we said is a qualitative assumption of the relationship between the exposure outcome and the covariates, and the same thing can now be translated quantitatively using the structural equation models. So here, for example, if X is representing our exposure or treatment, and this equation on the top shows us that the potential value of Z, right? So here X leading to Z, that's the arrow that we're talking about. And that can be translated into an equation to show, which is on the top, which says that the potential value of Z for an individual in the study population would be a linear function of X as the individual value of X changes, but U remains constant. That's what is now being shown as an equation. An individual's value of Z will change by beta times XZ units if we increase X by 1 unit, while U remains constant. So we have this through equations, we can translate our qualitative assumptions into quantitative measures of causal effects. that equation also asserts that Z will not vary with Y if U and X remain constant. And it is such kind of causal interpretations that distinguish the structural equations from the ordinary usual regression equations that we use. And because the regression equations essentially are represent only the association and not necessarily causation of the actual outcomes with the actual values of the covariates. And then if we keep the concept of structural equations in mind, we would be able to estimate the actual potential outcomes under various actions or exposures. And then we have various ways to improve our understanding of the causal inference, because which are through various methods of what we call as methodological modeling. And because typically in observational epidemiological studies, right, we do not know that we have a set of covariates that is adequate to support the claim of an unconfounded or an unbiased assignment mechanism. So even if we have, say, successfully adjusted for all the known covariates at hand, we may not be sure that there are some other hidden or unmeasured covariates that, if were included in our equations, would have altered the result. And so we have mechanisms, say, for example, sensitivity analysis, which provides us opportunity to actually look at the existence of such a covariate. So if there were other covariates, if there were other confounders that we did not measure, for example, how that would relate to the exposure assignment and the outcome. And if we included those in our analysis, how it would change the result. We also have more sort of complicated and complex modeling methods to look at various, to actually quantify the various biases, right? To quantify confounding, to quantify biases due to selection of study participants, due to measurement errors, and so forth. So the conventional sort of ways of analysis of observational data that we have in health sciences, where what we do is we apply various statistical methods, assuming that probably there is no confounding, or maybe just an unknown confounding. There's no selection bias and there are no measurement errors, right? But there is a possibility of violation of these assumptions, that there actually could be some kind of confounding that we did not adjust for. There may have been selection bias that we did not take into consideration, or there may have been measurement errors. And the violation of these can be addressed. So typically with discussion around, so what we do usually is we discuss, okay, how, if there was unknown confounding, if there was selection bias, and if there was measurement error, how would it have biased our statistical results, and what would have been the potential value of our effect estimates given that these were present. But then we also have various methods of actually bias modeling. So that's a whole sort of domain in itself that provides a formal way of assessing this uncertainty due to these questionable assumptions of bias. And there are various approaches that are available in bias modeling that includes the use of Bayesian analysis, the use of Monte Carlo sensitivity analysis, and so forth. So to summarize, what we have seen are various models or approaches, sort of the theoretical framework to make causal inferences, more so from observational data. We have seen that the sufficient component cause models provide us specific hypothesis about how the causal mechanism occurs, what is the interaction amongst various risk factors or causes for a particular outcome to occur. We have looked at graphical models that are very useful and that provide us with a qualitative assumption about the relationship between the various variables, between the exposure, outcome, and it helps us to identify essentially what could be the sources of confounding or bias when we are analyzing or when we are designing studies and the effect of exposure and outcome. And then we looked at the potential outcomes model and the structural equation models, which is basically provided us with a framework for a quantitative estimation of the effect. So we've seen these various approaches, and there's different approaches. They provide us basically with a complementary perspective, and these are employed or should be employed together in a meaningful way to actually improve the causal interpretation of conventional statistical results, specifically and more so in observational studies. Thank you.